Hey guys, I'm going to talk to you about observability. We talked about this a couple of lectures ago or videos ago. I have a new background, so my dog won't distract you anymore, even though he's on the ground. So it's not really like you're missing anything except for like the great view of my couch, which admittedly is quite comfortable, but you don't need to worry about that. So observability. I defined it before, but I'm just going to rehash it again. So essentially, observability is given a continuous time system. Or just a system. We're considering continuous time systems in this class. So given a continuous time system of, say, a nonlinear system where f and h could be nonlinear functions of the state x, the input u, or just time, this system is said to be observable in the interval of t0 to t1, and t0 being the initial condition, t1 being some time along the trajectory. If the trajectories of the input and the output, u and y, along this interval can uniquely determine the initial condition. Okay, so now what does this look like? Let me see if I can draw it here. So if we have a time trajectory, this is t on the x-axis, this is x on the y-axis, or x of t. We start with an initial condition here, x naught, at some initial time, t naught, okay? So let's change up the color a minute. So we have this initial condition right here. Then we have a trajectory out here, but we can't really measure the trajectory directly because we're using our sensors to measure the trajectory or measure the output. So if it's temperature, they're measuring and you're measuring it with a thermocouple, they're measuring a voltage differential, right? So what we can do is we can say that on this period here, we have an output and we have an input. So we have a u of t and a y of t. Okay, so now if this input and output, which we know because we're injecting the input and we're measuring the output, if we can take these values and back propagate to find the initial condition, then we can say that this system is observable. So if we can observe the initial condition, and then this, like I said, this trajectory right here is unknown, then our system is observable. Great. So now how do we figure out or determine whether or not our system is observable? Well, it turns out to be very similar. I'm not going to get into really the why, but one way to show why is using a duality argument, where you can say that one system is very similar to another system if you do some change of variables. So you can look at what's called the adjoint system. And then there's some properties between the adjoint system, the controllability and observability adjoint system, and the controllability and observability of the initial system. But I'm not going to get into that. If you take ECE 500, then you'll see that ad nauseum. But if we just consider, if we just want to figure out if our system's observable or not, it might change the design decisions or change the sensors that you would want to use to accurately measure the system. If you can't measure the full system, that might be bad. It might not necessarily matter, depending on the type of system that you're considering. But for our case, we want to consider the following system. And we're just going to consider a linear time varying system. So A and B are functions of time, U, and then we have an output matrix, C of T times X. Okay. And then the expression now this is called the Gramian matrix, but it is V of T not T1 is equal to, make this bigger here, oops, is equal to the integral of T naught from T naught to T1 with the state transition matrix tau T naught times the transpose of the measurement matrix or output matrix times the output matrix times again the state transition matrix dt. Okay, so just as with or very similar to the controllability matrix or Gramian, this expression is called, like I mentioned, is called the observability Gramian. And so it's similar to the controllability matrix. The next page. The system, say the LTV system, is observable if V T naught T1 has what? Right, full rank. Which is the same as saying the rank is equal to n, where n is the size of our system. Okay. And so then we can compute, naturally, we can, if we can compute this V, namely if we can find the state transition matrix and we have the measurement matrices, we can easily compute this, matrix here to determine if our system is observable. And the basic algorithm to do that is one, compute the state transition matrix, right? V T T naught. Two, evaluate the observability Gramian. And then lastly, three, is determine the rank of the observability Gramian. For numerical systems, this is pretty trivial. For symbolic systems, it's going to be kind of tricky because you tend to have to determine if the system is singular. So you want to look at you want to look at the row reduced echelon form of it, or you want to look at the determinant if the determinant equals 0, then you know that some of the lines are linearly dependent on each other. So if the rank is equal to n, rank of V, oops, move that guy, equals n, then we have observability, then observable, and then otherwise it's not, right? Cool. So also just like LTI systems, or just like the observer, the controllability matrix in Gramian. For LTI systems, there's some evaluations that you can do to turn essentially the Gramian, the controllability Gramian, into a controllability matrix for an LTI system, to determine if your system is controllable. Well, the same thing is true for observability. So for an LTI system, we have the following result. All right. Let's see, how much space do I have? Great. All right. So basically, the LTI system is observable for an arbitrary t greater than t naught, if and only if just like the controllability matrix, the rank of the observability matrix which we denote as L, okay? And this is a different form than the controllability matrix, but we have C, then C times A squared, all the way down to C times A to the n minus 1. Let's move that up a little bit. Great. Where, let's just put a comment over here on the side, where again, A squared is equal to A times A cubed is equal to A times A times A. Okay, so if this matrix, this L matrix, has full rank, then we know that our LTI system is observable. All right, that's all I had.